Let's do the extra practice problems for Chapter 3. And notice the given information that an AMU equals the 1.66 times 10 to the negative 24th grams, the speed of light, and h. We're given those constants. Number 1, what is the mass for the average potassium atom in grams? Now, to do these, you're definitely going to need your periodic chart. I have one here, but I would suggest you use the one in the front of your book. Number 1, what is the mass of the average potassium atom in grams? So you look on your periodic chart, and potassium is a K. That's the symbol. So you'd go to K on your periodic chart, and it has 39.10 AMUs, and we want to get that in grams. So we're going to put our AMUs on the bottom, whatever's here always goes here, and our grams on the top. And we're told at the top of the page that 1 AMU equals 1.66 times 10 to the negative 24th grams. And so notice you have 3 significant figures here, you have 4 significant figures here, so when you do your answer, you will have to answer it in 3 significant figures because you're multiplying or dividing, and when you're multiplying or dividing, you count your significant figures, and your answer has to be in the one with the least number of what you started with, and that would be 3 right here. So our answer is going to be 6.49 times 10 to the negative 23rd grams. Number 2, a specific isotope of silicon has a mass of 4.814 times 10 to the negative 23rd grams. What is its mass in AMUs? Is this the most abundant isotope of silicon? So first, let's start with its mass. Okay, we want this in AMUs. Whatever's here goes here, and we're trying to get to AMUs. We are given that 1 AMU is 1.66 times 10 to the negative 24th grams. So that'll make our grams cancel. We have 3 significant figures here. We have 4 here. So our answer has to be in 3 significant figures, which is going to be 29.0 AMUs. And then you look at your periodic chart, and we're looking at silicon, which is Si, and on your periodic chart it has 28.09 AMUs. So this is the answer to the first half of the question. The second half of the question is this the most abundant isotope of silicon? Well, this is what is on our periodic chart. Therefore, this is the most abundant form of silicon. So this is a heavier isotope, isn't it? And therefore, the answer to the second half of the question would be no. This is not the most abundant form of silicon because it's heavier than the one that's listed on the chart, which would be the most abundant form of silicon. Number 3, how many protons, neutrons, and electrons are in an argon 40? So you find argon on your periodic chart, which is all the way to the right. It's a noble gas, and its atomic number is 18. So that means, I'm going to write here argon 40. Its atomic number is 18, so that means it has 18 protons, it has 18 electrons, we know that, and it has 40 minus 18, which is going to be 22 neutrons. And so we established that by taking the mass number minus the atomic number, and that's what gave us the number of neutrons. Number 4, an atom has 35 protons, 45 neutrons, 35 electrons. What is its symbol, including the mass number? Well, we know that the 35 protons tells us how to find what symbol it is. So you look on your periodic chart, and you find who is number 35, which is bromine, Br. So we're going to put here Br, and then we add the number of protons plus the number of neutrons to get the mass number. So that's going to be 80. So the answer would be bromine 80. And that's the complete answer, because 35 told you where to look on the chart to determine what its symbol is, and then you add the protons and the neutrons to get the mass number. Number 5, light has a wavelength of 34.4 nanometers. What is the wavelength in meters and its frequency? So we have 34.4 nanometers. We want to know what it is in meters, so we have nanometers on the bottom. We have meters on the top. I like to give the big one a 1, so this is going to be 10 to the 9th. I know he's got it done the other way. I know the way he gave it in the book on page 76 was 1 nanometer equals 10 to the negative 9th meters. And if you wanted to do it that way, then you could flip-flop it. I just wrote it with the largest one getting the 1 and the smallest one getting a positive exponent. Anyway, your choice, either way. So you could have written this, I'll just write it the other way just in case. You could have written this with 10 to the negative 9 and a 1. Also, either way will give you the same answer. And so that's going to cancel, and that's going to give you to the negative 8th. Do it in your calculator, it's safer. But there it is in meters. And then we're asked, what is its frequency? Well, we know that the frequency equals the speed of light divided by the wavelength. And so the speed of light is given to us there at the top of the page, 3.00 times 10 to the 8th meters per second, divided by, we just figured out the wavelength in meters. And so that will give us an answer in 3 significant figures in per seconds, which we call hertz. And so that's going to give us 3 significant figures, 8.72 times 10 to the 15th hertz. And please, that's 1 per second, which is hertz. Please do this in your calculator. Don't try to do it in your head, please. Number 6, yellow light has a frequency of 5.1 times 10 to the 14th hertz. What is its wavelength? Okay, so we know that frequency equals C over lambda, and we are looking for the wavelength, so we're going to go lambda equals C over frequency. We know that the C, which is the speed of light, is 3.00 times 10 to the 8th meters per second. You don't have to have that memorized, but I do. And after teaching physics, it just happens. And the frequency we are given here is 5.1 times 10 to the 14th hertz, which we know hertz is 1 per second. And so when we do that, we will be left with an answer in meters. We will have 2 significant figures because this is given to us in 2 significant figures. So it's going to give us 5.9 times 10 to the negative 7th meters. And he didn't ask for it in nanometers, so you can leave it as meters there. If he asked for it in nanometers, then you would go ahead and further convert. Number 7. A photon has a frequency of 5.94 times 10 to the 19th. What is its energy? Well, we know that the energy equals HF. And notice H is given to us right there. So, and let's see, a photon has a frequency, so we're given the frequency, so we can just come up here and H is 6.63 times 10 to the negative 34th joules seconds times, the frequency is given to us at 5.94 times 10 to the 19th hertz, which is per second, remember. We have 3 and 3 significant figures. You're going to do all this in your calculator. Your answer has to be in 3 significant figures, so it's 3.94 times 10 to the negative 14th, and the per That should have been hertz, sorry. And the per second will cancel with this second, so you'll be left with just joules. And that's what you want because you're trying to find the energy in this particular photon. And therefore, your answer needs to come out in joules, which is an energy. Number 8, a photon has an energy. What is its frequency? Okay, so here we're still doing energy equals HF. But this time we're looking for frequency, so I'm going to solve for frequency. We are given the energy as 4.9 times 10 to the negative 15th joules, and we have H given to us at the top of the page, 6.63 times 10 to the negative 34th joules seconds. So the joules will cancel. We'll be left with per second, which is hertz. Your answer has to be in 2 significant figures because this is 2, this is 3. So you have to give your answer in 2. And so it's going to be 7.4 times 10 to the 18th. And it's per second because that's all that's left. So we're going to give that in hertz. And that tells us that we are putting our things in the right places. Otherwise, we wouldn't get that. Number 9, a photon has a wavelength of 94 nanometers. What energy does the photon have? So once again, we are looking for the energy equals HF. And the photon has 94 nanometers is its wavelength. And remember that the frequency equals the speed of light divided by the wavelength. And we need the frequency because we are looking for the energy, aren't we? And H is given to us. So let's find the frequency. So we have the nanometers, and we know that this is given in meters, 3.0 times 10 to the 8th meters per second. So this also has to be in meters. And this is meters. One of these is 10 to the 9th of these. So that's going to give me 94 times 10 to the negative 9th meters. And if I wanted to do that in proper scientific notation, I would make that 9.4 times 10 to the negative 8th meters. So I'm going to put that in here. 9.4 times 10 to the negative 8th meters. Meters will cancel, and I'll be left with frequency. And what I got from that was 3.2, because 2 significant figures, that should have 3 significant figures. But this has 2 significant figures. So this answer has to be in 2 significant figures. So 3.2 times 10 to the 15th. So now I'm going to take that up here, and I'm going to plug in H, which is 6.63 times 10 to the negative 34 joules seconds, times the frequency which we calculated from the wavelength, which is per second, so that'll cancel, and this will cancel, so we'll be left with joules. We have 2 significant figures, so our answer will have to be in 2 significant figures. So in 2 significant figures, it's 2.1 times 10 to the negative 18th joules. So we were given the wavelength, and using this, we could find the frequency because we were asked for the energy. We converted the wavelength to meters because we saw here this was in meters, so this has to be in meters. 2 significant figures, so this answer had to be in 2 significant figures. We took that, multiplied it by Planck's constant, which is given to us, and that gave us the energy in this particular photon that has this particular wavelength. Number 10, the electron of a hydrogen atom is in the N1 orbit. It absorbs light with a wavelength of 103 nanometers and jumps to the N3 orbit. So it went from N1 to N3, and in the process of doing that jump, it absorbed 103 nanometers. It absorbed light with a wavelength of 103 nanometers. Okay, so that's the wavelength of the light it absorbed. If the electron of another hydrogen atom is in 3, what wavelength of light must it emit to get back to ground state? So how much is it going to have to emit going the opposite direction? It will emit the exact same wavelength of light, because it takes 103 nanometer photon of light to make it jump up, and therefore when it's de-excited or jumping down, then it's going to release 103 nanometer light. Number 11, the electron of one hydrogen atom moves from N4 orbital directly to its ground state. The electron in another hydrogen atom moves from the N6 orbital directly to its ground state. We have one going from N4 back to its ground state. We have one going from N6 back to its ground state. Okay? That's what we have going on. Which electron releases a photon with the longer wavelength? Well, first let's look at this. Which one requires most energy? This one's going to, requires releases. This one's going to release the most energy, and therefore higher energy, higher frequency, lower wavelength, right? Higher energy, higher frequency, because of this, we know that. Higher frequency, higher energy, directly proportional. And then we also know this. So that means higher frequency, shorter wavelength. So when it asks this question, it says, which electron released a photon with the longer wavelength? It would be this one, because it's less energy, less frequency, therefore longer wavelength. And then it says, which photon had the higher frequency? It would be this one, because you would have higher energy, therefore higher frequency, shorter wavelength. But he didn't ask that. This would be lower energy, lower frequency, longer wavelength because of this. So we should be able to figure it out there. Okay, so the answer was that the electron from this, that did this jump, had the longer wavelength photon, and the one that did this one released a photon with the higher frequency. Now we get to number 12. And on number 12, it says, consider the emission spectra. It says, if a mixture of two elements has the following emission spectra, gives it to us, what two elements are in the mixture? Well, you're going to look up there and see which ones have the exact same spectral lines. And you'll notice that the first line is sodium, lines up with sodium. And the second two lines that are on that combination of the two elements would line up with the spectral lines of lithium. And therefore, the two elements in the mixture is sodium and lithium. Okay, now go ahead and finish studying this chapter. Prayerfully take your test, and then please read the first half of the next chapter. Have a very blessed week.